Have with us. Okay, so it's a pleasure to have with us Professor Philipp Hoehn. He will tell us about the progress in relational quantum dynamics. So you have, Philipp, 45 plus 15 minutes for your talk. So please begin.
Okay, yeah, thanks very much. First of all, thanks a lot for the kind invitation. So indeed, I'll be speaking about some progress on some phases of the problem of time. When I say progress, what I mean by that, so some phases, one could say the issues have been resolved, but in general, I mean, there's of course a lot more work that remains to be done on this topic. So this is just to put the scope of this talk clearly in advance. So I'm not claiming that the problem of time as a whole has been resolved here, but there has been some progress that has been made. And also what I should say, so this talk is restricted to non-field theory contexts, simply because in the quantum theory, of course, in field theory, everything is way more complicated. The phases of the problem of time I will be talking about.
Ulko-ovesta pääsee sillä nappulalla.
Sorry, I think there's somebody. Could you switch off maybe your microphone? Thanks. Some of the, the issues I'm going to be talking about, they've been discussed in the literature anyway in the context of non-field theoretic problems. Okay, I thought the talk was 60 minutes, so I have to probably accelerate a bit, but let's see how far we get. Okay, so just so we're all on the same page, just a nutshell review of the problem of time. So that's due to the fact that in diffeomorphism invariant series, or whenever you have reparametrization invariants, such as in general relativity, then your Hamiltonian is in fact a constraint. It has to vanish on physical states. And in the quantum theory, that means that states that you might consider physical of your theory, that they're annihilated by this Hamiltonian. And then, looking at this sort of naively, it appears as if we are somehow frozen formalism. It's naively like a Schrödinger equation without the DDT part or a constant DDT part, so that's zero. And so then often you hear that this leads to a timeless theory. Now, I would like to argue, in fact, that that's a bit of a misnomer. It's not really a timeless theory. It's a background timeless theory. So it just tells us that the quantum states we're going to be considering, that they don't evolve in some background time. So ultimately, the diffeomorphism invariance is, of course, about background independence. And so we shouldn't expect that our states evolve relative to some external structures. But it does not mean at all that the theory is devoid of any notion of internal time, and that's of course the whole basis of the relational approach to dynamics, to basically pick some dynamic degrees of freedom that might reside in this state, and then ask for how other degrees of freedom are evolving relative to this. And so that's the idea of how to extract then generally a notion of dynamics from such a seemingly timeless state. Now, just very few words about relational dynamics that we are going to be facing in the rest of this talk. So yeah, it's connected to what I just said. The basic premise here is that there is no external reference in the world, so that basically all reference systems or reference frames are actually internal and physical. And so we're going to be facing the question of how do we actually describe physics relative to some internal reference frame. And here, since we're interested in dynamics, how do we actually describe dynamics relative to some internal clock or some internal time degree of freedom. And another question that, of course, arises immediately is if we want to have a dynamical notion, for instance, of a time or temporal reference system, what is actually a good temporal reference system? So what I'm going to tell you here is not really supposed to be a rigorous definition of it. It's more to give you a bit of some intuition. And so the basic idea is that, a temporal reference system should ideally be in some sense, or loosely speaking, as non-invariant as possible under the flows induced by the constraint of the theory that actually generates some gauge symmetry, so basically reparametrizations. so that we can actually use these degrees of freedom to parametrize the orbits, or basically the gauge orbits, with dynamic degrees of freedom. And so then we have the notion of dynamical clock degrees of freedom, and then we might ask how other degrees of freedom actually evolve or change as these dynamical degrees of freedom change along the flow generated by such a constraint, and that gives us a relational notion of dynamics that in fact is invariant ultimately. Okay, so basically, clock degrees of freedom or internal clocks are in some sense gauge degrees of freedom. They're not invariant, but the main idea is, of course, that we use non-invariant reference degrees of freedom to compose them with non-invariant evolving degrees of freedom into some invariant other degrees of freedom. Now, with the problem of time, I mean, there exist many different sub-facets of it. I'm just going to touch on 5 of them that have also been discussed in these classic reviews by Kuchar and Isham about 30 years ago. There's many more than the ones I'm mentioning, but these 5 are the ones that I have something to say on. So one of the issues discussed there is that there exist, for instance, many different approaches to the problem of time, such as in particular relational approaches. 3 of them are so-called relational observables, and there exist these deparametrizations, and there exists this Page-Wootters conditional state formulation. And ultimately, the question is, of course, what's the relation of these different approaches? So some of my, okay. Do we have an ambiguity in dynamics, or so, which approach should we pick? Then Kuchar has raised 3 serious criticisms against the Page-Wootters conditional state formulation, basically arguing that it's an unviable approach. There exists another problem that you see often, that's the so-called multiple choice problem. That's basically the problem that if you use dynamic degrees of freedom as a clock, well, generically, which one are you going to pick? There will exist many different choices. They will in general not be equivalent. Then there exists the so-called global time problem that, in fact, in generic systems, you will not have monotonic internal time functions. What do you do then? And then there exists another problem that was raised by Unruh and Wald, where they argued that all realistic clock degrees of freedom, dynamical clock degrees of freedom, are such that they may run backwards. Now, if you're not familiar with all of these sub-facets of the problem of time, so the first aim of this talk is to make you familiar with them. So I'm going to serve you the problems that I want to then address later on, so that we understand what we're going to be talking about. And let's start with the first part. Okay, so some of the slides. Okay, so I will be talking now, give you a 1-page summary of relational observables, of these 3 different approaches to relational dynamics. And relational observables are basically a notion of observable that encodes how some observable, let's call it little f here, evolves relative to a chosen dynamical time variable t, where this t is then like the temporal reference system, a dynamical one. Classically, well, if we have our constraint surface, and then we have the orbits generated by, let's say, the Hamiltonian constraints. So basically, this t is then some function that gives you a dynamic parametrization of that orbit. And and these relational observables, they basically encode the question: what's the value of this little function f when this clock function t reads tau? So there exists a formalization of that was developed by Bianca Dittrich some time ago. It's not so important exactly how to derive this, but let me just phrase it here. So this is in terms of, so this alpha here is the phase space flow generated by the constraints on the constrained surface. Basically what you're doing is you're kind of flowing in some sense the little function f to a gauge fixing surface where t reads tau. And then you evaluate that function on it, but you can write it in such a way that that the function is ultimately defined on the entire constraint surface, and that it is in fact constant along the orbits generated by the constraint. So Poisson commutes with the constraints, where this here just denotes a weak equality, so it means it's 0 on the constraint surface. And so in that sense, it's a gauge invariant observable. So it commutes with the constraints, but it nevertheless encodes evolution of this little function f relative to this clock function t. And how does it do it? Well, you still have this parameter tau sitting inside of it here. So this guy here, this is now our evolution parameter. And basically letting this tau run in this observable is like taking the hypersurface here, the gauge fixing surface, and scanning through the constraint surface, if you wish. So, and that's a gauge invariant notion of evolution here. And now the idea is, so if you want to go to the, so actually this is also the reason why these objects are sometimes called gauge invariant extensions of gauge fixed quantities. Now, in the quantum theory, the idea is basically you promote such objects here to operators on the physical Hilbert space, where that's just the space annihilated by the constraints. And then you still have somehow an evolution parameter tau that runs and that somehow encodes the dynamics of the theory. So just maybe if you haven't seen such things before, just to give a bit of intuition. So in like the really probably the simplest possible example, a parameterized particle. So you can take a free Newtonian particle, you can parameterize it. So basically extend your system, you promote t to a dynamical variable, and then you write your action relative to some new gauge parameter s. You can convince yourself that this thing here.
Can I make a comment?
Yeah.
So if you could go back to the previous transparency.
Yeah.
Okay, I have to explain what's my point about. So I really don't like this that everybody, 100% of people working on this framework use this frame. You have to choose your clock function, blah, 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 what clock function says. If you look in this formula for the capital F, on the right-hand side, you can see the Hamiltonian. And
yeah.
actually, this is the Hamiltonian which gives us this evolution rather than the clock function. Of course, Hamiltonian is related to the clock function because this is a canonically conjugate variable. So, but in fact, all this evolution, just in one sentence, it is given by fixing any vector field on the reduced phase space. So given reduced phase space, you fix any, well, maybe preserving the, the Hamiltonian vector field. So you can fix
yes, I mean, at this point
any
here,
Hamiltonian vector field, and then it gives you, well, and then from this vector field, you can take a canonically conjugate function to be time, but it doesn't matter. What gives you evolution is this vector field that can be fixed arbitrarily. Okay, thank you.
Yes, I mean, here I'm not even talking about the reduced phase space. So here I'm really still on the constraint surface. But yeah, I mean, here the thing is that t actually does not have to be conjugate to the constraints. So this formulation here also encodes the possibility that t isn't, that this Poisson bracket here is not one. So I would still say that this is a evolution here at the level of the constraint surface of, it's telling me how f changes as t changes along the orbit. But maybe if it's, since it's only 45 minutes, let's maybe discuss such details later. Anyway, so here, just to come back to the example, so we have now then a reparameterization invariant action. And while you can consider, do a Legendre transformation, you see that there's a constraint. It's very simple. And in this case, you can ask, you can construct a relational observable, and you can just ask, for instance, what's the position of this particle, Q of the particle when this new dynamically rare freedom T reads tau. And while you can put this into that expression that I showed you on the previous slide, and you get the simple form here. This is a gauge invariant object that commutes with that guy with a constraint. So being gauge invariant, I can actually gauge fix it and without losing information. And a good gauge fixing, for instance, is setting this little t to 0. And if I do this, then the expression I get is just the solution to the equations of motion of the original unextended theory. So in that sense, the gauge invariant information in the extended system is equivalent. The relational information is equivalent to the original unextended one. And of course, you can quantize this. It's in a simple case. Okay, now let's come to a second formulation of relational dynamics, and that's often called deparametrization. There exist, in fact, many different ways in which you can do it. Yeah, the group in Warsaw, especially also Jurek and Wojtek and so on, have been working on such things also in the past. So here I'm just going to look at a particular way of deparametrizing, so it's not unique. So basically the idea is, so suppose we were given now some canonical data on our constraint surface or in the kinematical phase space. And basically, you can, first of all, do a canonical transformation that splits the degrees of freedom into pure gauge and constraint and into gauge invariant degrees of freedom. So using, for instance, the relational observables, in this case, this is a canonical transformation because the relational observables, they preserve Poisson brackets in a certain way, here I can turn the constraint into phase space variable, and then while t is just if I do it in this way, it's canonically conjugate to it. And if I do it this way, well, then I can just go and gauge fix the system, at least locally. So it might not work always globally, but then, for instance, I could set t equals 0. It's just the gauge degree of freedom, and I can solve the constraint. So in this way, I'm getting rid of the redundancy induced by the constraints in the description. And in particular, I'm just getting rid of my reference degrees of freedom, so the clock degrees of freedom. And I'm just left with basically these relational observables, but I'm evaluating them on the gauge fixing surface. So, you know, t and its momentum are no longer dynamical in some sense, they're just fixed. And then I get basically a gauge fixed expression of this gauge invariant object. And then, well, you can, basically that gives rise to a reduced phase space. And on this reduced phase space, you can look at the evolution of these gauge fixed observables in tau. And well, that's your reduced dynamics. And you could consider that as the dynamics from the perspective of the chosen clock. And well, often what one wants to do then is to quantize this reduced phase space. And like I said, there exist other ways of doing this too. And then let me discuss the third way of relational dynamics that's often discussed in the literature, and that's the so-called Page-Wootters formalism. And so here in the traditional literature on this, one considers a restricted form of a constraint, such as you split your total system in a clock C and a system S, and you consider the homotonic constraint to be of such a form where there's no interaction between the clock and system. So just for simplicity, and then one somehow defines clock states that satisfy this condition here that are monotonic in the dynamics generated by the clock Hamiltonian. And then you look for a conditional state formulation where basically you look, you take now physical states solving this constraint, you condition them on the clock reading tau, and then you ask for basically a property of some system observable. And then, well, you normalize in a particular way. Note that this here is in fact the kinematical inner product, not the physical inner product. And then, so this is kind of like a Born rule if you want. And then one interprets this as the probability, you know, for Fs taking a certain value when the clock reads tau. And what is also important is that if you look at the conditional states, so you take the physical state and you condition it on the clock reading, let's call this psi s of tau. It's not very hard to convince oneself that this thing actually solves the Schrödinger equation. So you have a reduced theory, and you can view that as the evolution of the system S relative to the clock C. Okay, and so now the question is, what's the relation of these three approaches? Well, as we will later see, they are related. Let me next explain the further problem, and this is Kuchar's criticism against the Page-Wootters formalism. And yeah, there's three of them. The first one is that Kuchar argued that this whole construction is incompatible with the constraint. So if you look at this kind of Born rule, as I discussed it before, because here we're talking about the kinematical inner product, but we use physical states, and then we have this object inside here, and this does not commute with a constraint. So this thing would throw the physical state out of the physical Hilbert space, and is therefore, you know, so Kuchar's reasoned is inconsistent with the constraints of the theory. Now, he then also argued that if you do a double conditioning, so if you look at something like propagators or transition probabilities, just basically extending the setup here, and the way you would do it basically, so you're looking for a probability, you know, what's the probability that whatever a particle is in position q prime when the clock reads tau prime, given that initially the particle was at q when the clock read tau. And basically it's kind of a double conditioning the way he interprets it, again in this kinematical way. And then he shows, well, if you do this, you get total nonsense, namely just a delta function. So there's no dynamics at all, just it's completely inconsistent. Now, then there's a third one that he raised, and that was to say that for Klein-Gordon systems or relativistic systems, it just gives the wrong localization probability. Basically, it just gives us a Schrödinger type, you know, probability density, which is not, you know, of the form of what we know from relativistic systems. So in particular, this here is a solution to the Klein-Gordon equation and not to a Schrödinger equation. And so, yeah, this was kind of heavy criticism that effectively ended research on the Page-Wootters formalism for a while, until about 10 years ago or so. And we're going to address those problems later on. So let me discuss the next issue that I want to talk about in this presentation. It's the multiple choice problem, and that's basically as I already said before. So, you know, in general, there exist many different possible choices for relational clocks, and they may be inequivalent in the quantum theory. So, for instance, yeah, you know, classically, you might have two time functions t1, t2. Then you can ask, you know, what's t1 when t2 is such and such, or the converse. But what do you do if these objects are actually operators? How do you relate them? In quantum cosmology, classical example is what's if, you know, t1 is like the scale factor, say, and t2 is, let's say, a scalar field. And then Kuchar, well, said, you know, there's many, the multiple choice problem is one of an embarrassment of riches. Out of many inequivalent choices, one does not know which one to select. And Isham was raising the question of whether these different quantum theories that we would get if you were to look for different clock choices, whether it could be seen as part of an overall scheme that is covariant, and was basically saying that a single Hilbert space cannot be able to encompass all of this. And anyway, the question is, how do we relate these different clock choices? Then the next problem I want to discuss is the statement that realistic clocks may run backwards. First of all, yeah, there's one thing that, of course, everybody knows. There exists basically no perfect clock for bounded Hamiltonians. You know, if we have a bounded Hamiltonian, then, for instance, there exists no self-adjoint clock operator that satisfies, well, it's conjugate to the Hamiltonian. That, of course, goes back to Pauli. But there's a somewhat refined version of this that was due to Unruh and Wald from '89. And they also showed that there can be no self-adjoint clock operator that satisfies a certain monotonicity property for bounded Hamiltonians. And basically, what the requirements that I set out is you have a sequence of states with increasing t, and you can view them, for instance, eigenstates of some maybe some projection operator and some interval of t. And then the conditions they impose is that if you have now that n is larger than m, and n refers to you know, the labels of t. So basically tn is a later time than tm, that then the transition probability for positive t, and here what I should say is this is formulated in Schrödinger quantum mechanics. So this t, this little t, is basically the background time. And then they look at the transition probability between these states. And then the condition they impose is that it should be non-zero for n larger than m, so that, you know, the clock can move forward for positive times, and that it should be zero for all positive times and all clock states that are basically smaller, so that the clock cannot run backwards. And so, well, they proved that such a time operator cannot exist. And so basically their interpretation of this was then that any realistic clock is such that which can run forward in time must have a non-vanishing probability to also run backward in time. And then they raised that as a problem because then they were wondering, well, then other variables might be multi-valued at a given clock reading. And in fact, this was one of the motivations for why they wanted to then look at unimodular gravity.
Maybe I can add one comment.
Yeah, sure.
This Pauli theorem is under very strong conditions obtained.
Yeah.
And it is a work by Galapon, which showed that weaker conditions, which are physically acceptable, allows to meet this problem of non-existing of this T operator.
So you're saying that one can sidestep that problem? You're saying one could have a self-adjoint T that is conjugate to H?
Yes, it's conjugate, but it's based on so-called positive operator valued measures.
Yeah. No, exactly. So I will come to that. Yeah. So
okay.
I mean, that's basically indeed how we're gonna solve also this problem down here. Yes.
Okay, fine.
Yeah.
Because also it's not that it will be self-conjugated, but if it will be symmetric operator, also can be constructed.
Yeah, exactly. So I mean, that's exactly how we're going to solve it through POVMs. I'll do that in a few slides. But thanks. Yeah. Okay. So well, the last problem, actually, in fact, I may not have time to discuss it if it's a 45-minute talk. Is the global problem of time. And that's basically the the problem that generally you don't have time functions that are monotonic. An extreme example is here the closed Friedmann universe with a massive scalar field. And for instance, if you pick, let's say, phi as your clock, and then you want to know alpha here is the log of the scale factor, and then you want to ask what's the value of alpha when phi is 0, say, well, you have a lot of different answers. So what do you do in that case? But yeah, okay. So these are the problems that I wanted to discuss. And there's some update on this that I want to discuss in the remainder of this talk. Basically, one of the things we will see is that these three different approaches to the relational dynamics, there exists a certain equivalence between them that I will hopefully manage to explain. One can also, using that equivalence, in fact, completely resolve Kuchar's criticism against the Page-Wootters formalism. Well, yeah, as I hinted at, this problem of that we just discussed, that realistic clocks may run backwards, can be solved with POVMs. The multiple choice problem, we have now developed a covariance framework for clock changes. And okay, this year the global time problem, I think I won't have time to discuss this later. Okay, let's start with the clocks run backwards issue. And indeed, basically, the way to sidestep it is to give up the idea that we have to deal with a self-adjoint T. And instead, we now use generalized measurements and in particular positive operator valued measures. And let me say a few words about those. I don't think I know the literature that you are referring to, Wladimir, but there exists, of course, various other works on this. And so basically what we're looking for is an operator valued probability measure. So suppose we're looking at a clock whose range is all of the reals. We're now going to look for some operators that are positive. If I just integrate them over some interval of the possible clock readings, it's a positive semi-definite operator, and they're normalized. If I integrate over all of the reals, then I get 1. So then I can basically interpret these objects here as a probability measure. In general, these different effect operators, they will not be orthogonal, even if the time intervals over which I'm integrating are non-intersecting. So for self-adjoint T, yes, they will be orthogonal, but not in general. So in particular, these objects, they will in general not be projectors. And then what we want to have is that these effect operators that define the POVM, that they're monotonic, that they satisfy a certain covariance condition with respect to the clock Hamiltonian. So which reads like this. So basically, if I just evolve with the clock Hamiltonian by t, then I just basically change the label of this effect operator. In that sense, they're actually monotonic. And how can one actually construct these objects? So here, we want to know what are these basically these effect densities or these probability densities, if you want. They're going to be constructed using certain clock states. The sigma here, those will be like degeneracy labels for the clock Hamiltonian. For example, in relativistic case, the sigma may be plus minus, like positive negative frequency modes. And in these cases, what you can do is you can construct these clock states using the spectrum of the eigenstates of the Hamiltonian. And in this particular form, so schematically, and it's not hard to see that they will satisfy this monotonicity property here. And what are these states really? I mean, they're nothing but coherent states for the group generated by this clock Hamiltonian. And now we can put these states together, in terms of in these effect densities or these probability densities. And then since we have a probability measure, we can consider also moments of that probability measure. And the moments, well, they define operators, these nth moment operators. Well, where they are of this form, and they satisfy generalization, for instance, of canonical conjugacy. At least when the clock is unbounded. When you have periodic clocks, there's a few subtleties, but I'm not going to discuss them here. So for unbounded clocks, they satisfy a generalization of canonical conjugacy in that form. Now, the price you pay for sidestepping that issue is simply that in general, well, we will have a consistent probabilistic interpretation because this here defines a consistent probability measure for the clock states. But these nth moment operators, they will in general not be self-adjoint. They will be symmetric, but not self-adjoint. In particular, these clock states T here, they won't be orthogonal in general. So they are not in general perfectly distinguishable, and they will also in general not be eigenstates, for instance, of the first moment operator. So this is a generalization of the notion of self-adjoint observables. So self-adjoint observables, the spectral decomposition of a self-adjoint clock operator falls, of course, is a special case of this, but this here is much more general. And this can handle in particular bounded Hamiltonians. So just to give you an example, so in relativistic systems, we will of course often see something like this here, like minus pt squared, it's bounded, well, in this case from above. You can construct these clock states, for instance, in this form here. I have a theta function just to separate positive and negative frequency modes. They're not exactly orthogonal, but they satisfy covariance condition. And for instance, you can look at the first moment of this POVM, and you can prove that it actually is equal to this object here. It's not self-adjoint, but well, a symmetric operator that coincides with a symmetric quantization, for instance, of this object, which classically is canonically conjugate to the Hamiltonian. So this is the notion of clock states that we're going to be using in the remainder of this talk. And in this way, we will also handle clock systems with bounded Hamiltonians. Okay, let me now come to the question of the relation of these different approaches to relational dynamics. And so this is, well, the relation goes under the name of the trinity of relational quantum dynamics that we've established. So before I go into this, so basically what we now have is that the formulation in terms of relational observables at the level of Dirac quantization is something that you can view as a clock neutral picture. And that is in the end equivalent to particular quantum deparametrization. That's not always equal to the reduced phase space quantization, but it's always unitarily equivalent to the Page-Wootters formulation. And just to give you a bit of intuition of what this means, let me draw some analogy with relativity theory. So as I said, we are going to deal with something that we call a clock neutral structure, or more generally something like a quantum frame perspective neutral structure. So what's the analogy in relativity? So, and that's basically tensors. So if we just think about tensors abstractly as multilinear maps, I mean, they're just they're reference frame neutral objects, because of course they encode the physics as experienced by any local frame. So we can think, for instance, of a stress energy tensor, which is a map from two copies of the tangent space, let's say at some point x, to the reals. And if we want to know the numbers that some local observer would experience when doing some energy momentum or stress measurements, well, what do we have to do? We have to contract that tensor with the corresponding frame vectors, let's say some tetrad. So, and in that sense, of course, you know, the tensor encodes at once all the different possible frame choices, and yeah, you just have to choose a frame in order to spit out some numbers that have physical meaning. And we can now think about tensors really abstractly. And here I'm going to use abstract index notation as Penrose. So mu, nu are now not the components in some coordinate system, but just signify that this object is a map from two copies of the tangent space to the reals. And well, it's a frame neutral description of the physics in the sense of what I just said before. And then we can basically pick the tetrad vectors, again, understood in terms of the abstract index notation, as a coordinate map into the frame perspective of the corresponding observer if you want. So we just contract, or, you know, yeah, I mean, you can call it contraction if you want, of that abstract object with these frame vectors and with these frames. And that, of course, just spits out numbers. And those are the numbers that the observer would measure. And this here you can then consider basically as the internal perspective of the frame on the stress energy tensor. So the reason I'm stressing these things that are, of course, well known is that we're going to be seeing something very similar in the quantum theory. And basically the idea is that we're going to view generally the Dirac quantized theory and also the Dirac observables on the physical Hilbert space as some basically frame neutral description for the subject of relational dynamics. We just call them clock neutral, but more generally like reference frame neutral. And the reduced, like the internal perspectives, they're going to be like the quantum reduced theories. And the properties are going to be very similar. In particular, we can, of course, also invert this coordinate map and then go from, you know, from the internal perspective back to the frame neutral one. And this is, for instance, how we're going to develop frame changes later on. So since we're going to be talking about the Page-Wootters approach, also I'm going to do the same restriction as in the Page-Wootters literature. So we're going to look at the special case where the constraint is of this form. So it splits into clock and system without interactions. The clock Hamiltonian can be a generator of the translation group, or maybe a U1 if it's periodic, and HS can be whatever. And this encompasses, well, vacuum, Bianchi models, well, certain isotropic models, relativistic particle models, and so on. So it's, of course, not completely general, but it does encompass a set of models. And yeah, let me start with a clock neutral picture. So here we were talking about these relational Dirac observables before. What we're going to do now is basically the analog of, so we're going to use these covariant clock POVMs. And that's like choosing classically a clock T that's conjugate to the Hamiltonian. If you do this, well, the power series here simplifies to this form. And basically all we need in order to quantize this is a notion of this T to the N. And well, that we're going to do in terms of these covariant POVMs, so these moment operators. And then you can quantize these relational observables in this form here. So this is basically a quantum version of the power series. That's the, you know, the proposal for how to do it, at least at some formal level if you want. And here we use the covariant clock POVM. And you can show that you can rewrite this whole thing in this form here. It splits into these, in the end, super selection sectors, for example, positive, negative frequency modes. And then you basically have a conditioning on the clock reading tau then you have the system observable that you're interested in relative to the clock. And then what you're doing is you're just averaging this whole thing now over the group generated by the constraint. And so it's a particular group averaging, it's an incoherent group averaging, and it's called G-twirl in the literature on quantum reference frames. So formally, that thing is a strong Dirac observable. It commutes with the constraints, similar to what happens in the classical case. But you still have a notion of dynamics because this T here, this is just a label that can now run. It satisfies a bunch of nice algebraic properties that I, however, don't have time to discuss. So it's just to give you a flavor of how I can do this. And now let's go to the Page-Wootters formulation and show that it's actually equivalent. And then I will go to the deparametrizations that are a little more complicated. So what we're going to do is in the Page-Wootters formalism, there was this conditioning of physical states on the clock reading. And what we're going to do is we're going to define this as a map. And we consider this as the map from the clock neutral physical Hilbert space into the reduced Hilbert space of the system in frequency sectors sigma, say. And that is what we consider the internal clock perspective on the dynamics of the system. And basically, you can view this map R here, this conditioning map, as being the quantum analog here of this coordinate map in relativity that I gave you before. And then, well, if we throw this object here on physical states, so these are like the frame neutral objects, I'm going to map that now into a particular temporal reference frame perspective, the clock, and then, well, as before, this thing is just going to satisfy the Schrödinger equation. But what is crucial is that just like in relativity, this map is in fact invertible. And now if you look at this map, at first it seems, why should this be invertible? I'm just projecting on something, so that throws away information. But the key to remember here is that this thing now acts on the physical Hilbert space, and the physical Hilbert space satisfies constraints, and we're just conditioning on certain kinematical properties, and this is nothing but a gauge fixing. So, there's redundant information in physical states. So redundant kinematical information, there's due to the gauge-induced constraints. And what this does here, it's basically just getting rid of redundant information. It's not throwing away any non-trivial information. And that's why for physical states, it turns out that this thing is actually invertible. And what you find is, that you can, for instance, throw this on these relational Dirac observables. You can basically conjugate it with this map. And it turns out that this spits out these Schrödinger, or these little FS, so the system observable. So there's a bit of fine print to it. There's more details to it. So it turns out in general, there's no unique FS associated with a relational observable. So you get in general a projected version of that. You can ask me later about it, but it's completely consistent. But it's too much detail to put into these slides. Basically, the idea is now that you can think of this FS like it's like the analog of this TAB in relativity, like the contracted version of the stress energy tensor, and this object, the relational observable, is like the perspective neutral T mu nu. And what you can also show is that this map here is in fact an isometry. It's invertible, and it preserves inner products. So, and here we're now talking about the physical inner product. So evaluating a relational observable in the physical inner product on the physical Hilbert space is equal to evaluating the this little fs in the inner product of that Hilbert space. And in that sense, we have a full equivalence between the reduced state formulation of Page-Wootters and the physical Hilbert space formulation. And another way to think of this is that, what I have here, that these objects, they're like the manifestly gauge invariant formulation of the dynamics, and these formulations, the reduced ones, are like the gauge fixed formulation of a manifestly gauge invariant structure. Okay, and now I'm wondering how much time I have, so I might skip this part. If how much time do you have left?
You should have, say, a quarter, okay?
A quarter. I'm wondering whether maybe I'll just skip this next part, because Yeah, so it works very similarly. So basically, let me just summarize it in a few words. So here, this is just the classical deparametrization. And we can now do a quantum analog of it. Basically, the quantum analog of this canonical transformation that splits degrees of freedom into pure gauge and pure and constraint and pure gauge invariant ones. You can construct the analog of that. And then, well, you do basically the analog of the gauge fixing. Again, it's like in the Page-Wootters, it's conditioning. And in the end, you get a different reduction map that a priori looks different than in the Page-Wootters case. But what you get is basically, you just get now the Heisenberg picture observables and Heisenberg picture states. And well, then it's kind of clear that they're unitarily equivalent. So here, one can then say more precisely what the quantum analogous structures are of certain classical structures in the symmetry reduction. But let me maybe not go into this. So basically, this procedure that I'm skipping is like the quantum version of the classical procedure of phase space reduction through gauge fixing. And well, one can then, of course, ask the question whether these two procedures commute. So if I first classically gauge fix, go to reduced phase space, then quantize by reduced quantization, or whether I first do Dirac quantization and then I do this, this quantum deparametrization. And well, of course, in some cases that is true, but in general it's not. And well, that of course has to do with the fact that in general Dirac and reduced quantization are not unitarily equivalent. But basically the novelty here is that we have now a systematic map that tells us how to relate the Dirac quantization to reduced quantization. It just turns out that the observables are not always having the same spectra in the two routes. But let me maybe then not go too much into that. Yeah, basically the statement now is there is an equivalence of this relational dynamics in terms of relational observables on the physical Hilbert space, then in terms of the reduced structure in the Page-Wootters formulation and this quantum deparametrization. And the main message is that this one here, the Dirac quantization, or the clock neutral one, that's like the manifestly gauge invariant formulation, whereas the reduced theories are really like gauge fixed formulations, but they contain the same information. Okay, let me maybe skip the periodic clocks and let me say a few words on the Page-Wootters, on the criticism against the Page-Wootters formulation that Kuchar raised. So remember from before, his first criticism was that these probabilities are inconsistent with the constraints because the object doesn't commute with constraints. And well, here we have an inner product of the kinematical, not the physical Hilbert space. But the Trinity equivalence shows us that actually the physical inner product, the evaluation of this relational observable, in fact, what I should say is that the top line here is equal to this manifestly gauge invariant formulation, and that's equal to this here. This basically tells us, I guess here I wrote it down, but I just wanted to say, you can write this, you can basically view this form here that has been used in the Page-Wootters formulation for the probabilities. You can really interpret that just as a gauge fixed formulation of a gauge invariant way of formulating the probabilities. So in that sense, it's absolutely not in conflict with constraints. It's completely consistent. And we have a consistent probability interpretation for relational observables thereby as well. So that's another interesting effect, that this equivalence with the Page-Wootters formalism equips relational observables with a consistent conditional probability interpretation. Yeah, okay, so that's basically what I just said. Now let's talk about the second problem that he raised, that you get wrong propagators or transition probabilities. That's basically what he does here is just not how you should be doing it, because that's indeed in conflict with gauge invariance. And if we instead start directly from the physical Hilbert space now using the equivalence, we can just formulate probabilities and transition probabilities at the level of relational observables in a purely gauge invariant way. Without going into the details, you can then, using the equivalence with Page-Wootters, write it in terms of equivalently of the Schrödinger states. It takes, you can also generalize it, much more general than what Kuchar was considering. turns out this is always what you want to get. It's always the right answer. And if you restrict it to the special case that Kuchar was considering, where you look at particle position relative to some clock, then you find, oh, you always, in fact, you get the right transition probability. And basically, so that completely resolves the criticism. And the way you do it is just by insisting on manifest gauge invariance and then using the equivalence with the reduced formulation in terms of Page-Wootters. So that's maybe quite quick the way I'm saying it, but that's really the upshot. So there's no, if you do it right, you get it all consistent. Now, there exist previous proposals for getting the right transition probabilities by various groups. Let me just say very few things about it. Both of them actually modify the setup as discussed by Kuchar, because both, in fact, introduce additional degrees of freedom. So they modify the dynamics. Here in this paper, they introduce ancilla systems that kind of record time measurements. In this case, Gambini, Pulin, and so on, they introduce additional degrees of freedom to use relational observables as clocks for other relational observables. Yeah, so in this case, you also only get an approximate resolution of the problem. In this case, you get an exact one, but like I said, you modify the Hamiltonian, you introduce additional degrees of freedom. So if you really want to resolve Kuchar's criticism without introducing any additional structure, then well, the Trinity gives you that resolution. Now, yeah, so there's also, one can also resolve the third criticism that for relativistic systems, you get, well, if you do it naively, the wrong localization probability. So this aspect is a little more subtle than the other two criticisms, and that's because, what's the localization probability in relativistic quantum mechanics? There's no completely well-defined notion of it. We, of course, have a Klein-Gordon inner product, but then we would have to restrict to positive and negative frequency modes. But ultimately, the best localization probability that we have is essentially Newton-Wigner. And what you can show is if you use, instead of the naive T, like the inertial T, if you want, but you use instead a covariant clock POVM, then what you find is you get a localization probability, well, that's of a Schrödinger type, but it's of a Schrödinger type in the Newton-Wigner sense. So you basically get a Newton-Wigner wave function. And so the probabilities that you find are really Newton-Wigner type localization probabilities. And this is in fact also consistent with a physical inner product, which this here is not. So in that sense, it's an approximate localization probability, but for relativistic mechanics, that's basically the best possible thing you can do. Of course, if we want to have anything more accurate, then we would have to go to field theory. But for the finite dimensional setting, that's basically the resolution, the best possible resolution there is. Now, so that's all to say that you can resolve these criticisms, and basically that the upshot is the Page-Wootters formalism is a viable approach to relational dynamics. It's equivalent to relational observables, and like I said, in return, it equips relational observables also with a nice probability interpretation. So maybe I can still say a few words on the multiple choice problem. Do I still have maybe 5 minutes?
Okay.
And then I'll skip the rest. So let me just draw again this analogy with covariance and relativity. So this is what I showed you before. So we had this kind of frame neutral description in terms of abstract index notation tensors. Frames basically define your coordinate map into a particular perspective. Yeah, I mean, we now have seen this kind of works in the quantum theory too. Now, yeah, tensors are in some sense a description of physics before a choice of frame has been made at the abstract level. And now, of course, because it's frame neutral, we can, of course, choose a second frame, for instance. And so let's call that E tilde. And we can now do, of course, basically the same steps that we did here and going to a different frame, internal frame perspective relative to the second frame. And now, since these maps here, these tetrad maps are invertible, I can also invert that, that arrow here. And so that defines me then a map from the internal frame perspective of E tilde back into the frame neutral description, and then I can map it forward into the internal frame perspective of E. And well, that gives me basically a direct map from one internal frame perspective to the other. I mean, that's a coordinate transformation ultimately, and that's conjugation with Lorentz transformations. And the Lorentz transformation have this form here. They're defined basically by the inverse and the forward map of these tetrad frame or the coordinate maps. And in that sense, yeah, the change of internal frame perspective always, of course, proceeds via the frame neutral description in terms of such coordinate transformations, which here are just like local Lorentz transformations. And we're now basically going to see the same thing or the completely analogous structure in the quantum theory. It's just that we're going to interpret the clock neutral theory, the Dirac quantized theory, as being that object, and then the reduced theories are like these internal frame perspectives, and these R maps, these reduction maps that I showed you before, are like these E maps here, and otherwise it works in the same way. So, and that's the basic idea for a quantum clock covariance, that, for instance, coming back to my opening slide, that we don't consider the state psi phys as being a timeless state, but we consider it rather as a clock neutral state or an internal time neutral state. It's like a description of physics prior to having chosen a temporal reference frame, relative to which we will describe the dynamics of the remaining degrees of freedom. And why is that possible? Well, it's possible because the physical Hilbert space carries an induced redundancy in its description in terms of the kinematical data as you know, induced by the constraints. And so there exist many different ways in which we can describe the same invariant physical states. And we will associate these many different ways with different clock choices. And then these reduction maps that remove the redundancy, we will, relative to different clock choice, we will interpret them as the quantum coordinate maps into a particular clock perspective, and those can be inverted. And so basically, now if we have a setup, let's say where we have two possible clocks like C1 and C2 and some evolving system S, given with a constraint like this, again, let's say there's no interaction, then basically this setup here is the complete analog of what I showed you in the relativity situation. The physical Hilbert space, like the clock neutral one, okay, you might have to split it up into frequency sectors, but otherwise per frequency sector, you can construct these quantum coordinate maps, you know, these reduction maps that are invertible that I showed you before, for instance, in the Page-Wootters construction, and you can concatenate them in the inverse map of one with the forward map of the other, and that gives you a map from one internal clock perspective back to the via the clock neutral theory forward into the new perspective of another clock. And you can think of this map lambda here really as being the analog of this Lorentz transformation that I showed you before. So like this, you know, kind of in the obvious way. Well, you can throw this on states, and you can throw this on observables also in the obvious way. The main thing is we're always describing the same physical situation, just from different perspectives, just as in relativity before, we described, you know, there the same stress energy tensor, but in different internal or local frame perspectives. So of course, you know, the stress energy tensor will look different in relative to different frames. And we have the same situation here in the quantum theory. And just like in relativity, things will look different in different frame perspectives. You have the same thing here in the quantum theory. One main thing that is different, it turns out, is that, for instance, entanglement depends on the frame perspective. There's been a lot of work recently on explaining that. So correlations or even superpositions depend on which frame perspective you choose, and that's not only for clocks, that's more general. You can show that there's a certain quantum relativity of comparing readings of different clocks and synchronizing them. And also, one can also, for instance, have that relative to one choice of clock, the evolution looks like temporally local. In another, it might look like a superposition of time evolutions relative to one another. So I don't have time to illustrate that here. It's just to give you some flavor that there are really some funny things that happen. And for instance, that temporal locality is frame dependent is just basically the clock analog of the statement that entanglement depends on the quantum frame more generally for spatial reference frames. And anyway, there's other effects that one can study, but that's just to give you an intuition that you can actually get some funny effects with in this clock covariance. And there's one reason why these things actually happen. Let me just illustrate or explain that in one slide, and then I think I will finish. It's that the notion of what you mean by subsystems in the gauge invariant setting is actually frame dependent, because now we define, what we mean by a subsystem, like if we have systems A, B, C. So for instance, what C is relative to the system A is defined in terms of relational observables of properties of C relative to A, or what C is relative to B is defined in terms of relational observables of C relative to B. And it turns out that the algebras of these relational observables inside the total invariant algebra, they do overlap, but they're distinct algebras. They are non-coincident algebras. And that basically means, what different subsystems mean when they refer to others in a gauge invariant way is frame dependent. And basically, for that reason, if you probe one and the same physical state for correlations in different frame perspectives, you're going to be probing different observables. And of course, that means you're going to get different correlations. So that's just like a very brief explanation for all of that. And I think I'm going to skip the rest. And I think, so that's about the global problem of time. And here, one other thing is that all of what I said can in fact be generalized to general unimodular groups. So it's not only true for like one-dimensional groups, such as reparametrization invariants, but you can do it, very generally. And that has been just done last week, in fact. So the trinity, this equivalence holds for general groups, in fact, as well. And also these quantum reference frame changes, all of that works basically the same way for general groups. But let me not go into this. And let me just maybe conclude with a slide here. That's kind of a summary of the topics that we've discussed in this talk. And I'm sorry for going over time. So thanks very much for your attention.
Okay, thank you very much, Philipp, for your inspiring talk. And now we have some time for questions.
Okay, could I also say a few words?
Okay.
We are solving for since many years, in fact, something as theory of quantum time, which we call projection evolution. In some sense, a few results you showed are similar to relational dynamics. This. But,
well, I mean, this is relational dynamics here.
Sorry?
This is relational dynamics here.
But what we are doing, I can say that one of the point, sorry, I have a problem with flow. One of the point is that we are able to obtain self-conjugated time operator, omitting also Pauli restriction in this sense that we introduce as a canonically conjugated to time operator is not Hamiltonian, but fourth component of linear momentum. It seems to be natural. It is a generator of geometric translation in time. But Hamiltonian is related to this momentum, usually by through simply equations of motions. This leads to a very natural treating of time. Very similar thinking is as in classical dynamics. There is no problem with covariance then. There is no problems with uncertainty principles, time, energy, also through these equations of motions. For example, how do you think about this uncertainty principle? How you are able to obtain it in this relational?
I mean, well, it depends a bit on what sort of uncertainty principle you're referring to, but there's in principle no problem at all, because there exists a lot of work on uncertainty. I mean, I guess you're talking about something like time, energy, uncertainty relations in some sense.
Yes, yes.
Yeah, so I mean, there exists a lot of works on that in the, so I haven't worked on that myself. Let me try to, okay, how do I go back here? So, I mean, you know, in this context of these covariant POVMs, okay, sorry, I'm trying to find the, okay. I'm trying to go back to the slide. I just, okay, how do I do this? Okay, anyway, yeah, so there exists a lot of work on that in the quantum metrology literature, because actually these covariant clock POVMs that I was referring to, they come from the quantum metrology literature, and there these time uncertainty relations are very important. And basically, yeah, the thing is, I mean, you can derive a whole bunch of consistent ones. So this would, yeah, okay, no, sorry, how do I go back to the, okay, anyway, so yeah, it's basically in this literature here, especially by, yeah, Bush and so on, Caves, Braunstein, and so on, there exists quite some work on time uncertainty relations, and there's no problem. I mean, the reason is ultimately you're dealing with it at the level of just purely the clock Hilbert space, so you never really have to worry about the evolving degrees of freedom. So yeah, I mean, basically, you know, because these clock degrees of freedom are, you know, in some sense conjugate to the Hamiltonian, on the clock Hilbert space, you can formulate these time uncertainty relations in a very similar sense to how one usually does it in textbook quantum mechanics. Of course, the only thing is that it's somewhat more general, because here you're dealing with, you know, with POVMs, which are such that these operators are not necessarily self-adjoint, but that's not a problem.
Yeah. Yes. But you know about such effects like time interference, which is now experimentally now.
Which is what, sorry?
Time interference. Objects, yeah. Not speaking very simply, you have objects which are localized in different times, and wave functions can interfere okay. Together. Mm-hmm. Such effects are known since a few years, I can say. Experimentally, yeah. It is no effect. In such approach as you show, it's practically impossible to show such an effect.
Why? I don't.
No,
think
for
so.
example, you can reproduce a typical interference like in Young experiment through 2 times holes. Are you able to do it?
Well, so I mean, are you telling me that? So I mean, if it's experimentally proven, I guess it's formulated in standard quantum mechanics, textbook quantum mechanics, right?
No, it's observation that if you have it is observation with these experiments are done with very short laser pulses.
Okay, but
they are shortened then. That is, it is possible to get something like interference typical to Young experiment in normal waves, where these holes are different moments of time.
Okay, but I mean, how is it theoretically described? Is it described? I mean, so I'm not familiar with those works, but is it described in terms of
in terms of fringes, different?
No, theoretically, I mean, is it described in terms of?
No. In experiment, it's described as a energy spectrum.
But does there exist a theoretical description of this in terms of quantum mechanics?
Not quite clear. There are some trials, but it is not quite clear how to do it. In this formalism we are developing, it's possible to do it very easily, but it's not standard.
I mean, obviously, since I don't know about those works,
yes, okay.
I cannot give you a definite answer. But coming back to other things that I said before, where I was talking about this clock covariance, I mean, what we can certainly have is that in these internal perspectives, we can have notions of non-local
non-locality in time. Okay.
Sorry.
Non-locality in time, simply you can have. Yes, it's clear.
Yeah. So we can have that, and I mean, so I would think that probably such effects should be also, as long as they can be explained in terms of quantum theory, I wouldn't see a reason why it shouldn't be possible to encompass that with this framework here. No. I don't see a reason.
And if I have the last problem, experimental problem, you know that EPR pairs, which Einstein-Podolsky pairs, there is experiment between these two islands done, La Palma and Tenerife, which allow, it shows breaking of causality. What do you think about this?
I don't think it shows breaking of causality, no? I mean, it's just the standard EPR situation. You have entanglement, but I don't see how
to have causality, you should have sending of information with velocity which is 90 times velocity of light. That is to correlate both effects.
No, but I mean, they have not shown that you have that you can communicate superluminal. That's not true. So
that is obviously it's a reason that causality in this sense is not clear. What to understand?
No. I mean, it's just generating of entangled pairs from one island to another. So I happen to be at the institute that carried out this experiment, and that's just entanglement across. You have an entangled pair. But entanglement doesn't mean that you can communicate faster than light. I mean, it's
no. Obviously, you are right. But changes. But this type of communication, it's not communication. In fact, this correlation exists. And if assume that if this correlation is not the type of sending something that one object knows about another one, it needs more or less 90 times velocity of time.
Excuse me.
No. I mean, it's just standard entanglement in that case. There's nothing violating causality there at all. I mean, it's just standard entanglement. It's distributing an entangled pair over some spatial distance, that's all, but there's no violation of causality, in particular because you're of course generating the entangled pair locally. So there's a source where this comes from. There's an emitter that's creating that entangled pair. There's no violation of causality there.
Excuse me, Andrei, perhaps we give chance to other people because we're running out of time. So further questions, please.
Yes, perhaps I will have a question about the formalism.
Okay.
Yeah.
So the gauge freedom of this Hamiltonian constraint systems is interpreted as the freedom, the choice of internal time, right?
In some sense, yeah.
And now you introduce this relational observables, which clearly depend on the time because you use this capital T. This is some time. So in this sense, they are not gauge invariant. That they depend on the time. To my mind, just let me finish. So to my mind, this whole idea of relational observables is just a poor brother of the reduced phase space approach, because that's what you do. And now, having said this, I have a very specific question. Could you be more specific? What is actually gauge invariant? That is choice of clock independent dynamical content of the Hamiltonian constraint system. Like give me something like, I don't know, let's say volume operator. and the spectrum of the volume operator, which is a dynamical operator, right? Something. What is gauge invariant dynamical content? I think that's the key question. Well, and I haven't seen an answer to this.
Okay, so first of all,
I know it's a difficult question, so.
Well, more or less. So let me maybe start with the first one. So there's some. Okay, so I have some appendix. Maybe I'll just go to that appendix to come to your first one, because you were asking about the time. Yeah, the choice of time is, so I mean, it's a very good question. Okay. Anyway, so this was appendix material. So basically the statement is, and indeed I didn't explain that in this talk, is in which sense I view, for instance, the algebra of Dirac observables in a frame independent way. And basically, let me just maybe go a few slides forward. It is as follows. So you get, or what you get is, you can write the entire algebra in the setup that we have of APHIS in terms of relational observables relative to one choice of clock or to any other, in fact. So if the clocks are global, let's restrict to that for simplicity. So basically the relational observables, what they do is, because they have this parameter tau inside of it, you know, I can let the tau run. If I let the tau run, I have a family of Dirac observables. So that means this actually defines me an orbit in the algebra APHIS.
Yes, but just to say, so what you are saying about the algebra of Dirac observables, there are no more observables. This is the algebra of Dirac observables, the invariant algebra.
Yeah, I'm talking about that one. And the main point is that, so this is what I'm trying to illustrate with this colorful slide here, that you pick one clock. If the clock is global, you can write any element of APHIS, at least informally speaking. You can write it as a relational observable relative to that clock. If you have a second clock in your system that's also global, that means you can write likewise every element of APHIS as a relational observable relative to that second clock, and so on. And now, and so this is something that even also holds for general quantum reference frames in the setups that we've constructed. So this is something that you can prove by, well, you get a certain isomorphism between the reduced algebras and this APHIS, and we have these embedding maps through these reduction maps. And basically, that means you have some abstract observable O, say, an element in APHIS. An abstract element will lie on many different orbits at once, where the different orbits correspond to different quantum reference frame choices, or in our context, to different internal time choices. So it means an abstract element of the algebra of gauge invariant operators, so an abstract Dirac observable, has in fact many different physical interpretations. So I can interpret it as a relational observable of some degrees of freedom relative to particular first choice of clock, but I can also interpret it as a relational observable relating some other degrees of freedom relative to another clock. And so in that sense,
yes, this is clear. So in a sense, you can assign different dynamical meaning to a fixed Dirac observable. I mean, yes, that's the key. Yes, go on.
Yeah. So and basically, the statement is that the choice of clock provides the context in which I interpret this abstract observable. So it's a bit similar to what I said about relativity, where you have these abstract tensors. And if I want to give physical meaning to them, well, I have to somehow, you know, choose some frame. So it's a bit similar to that. It's just that here, yeah, I mean, without providing such a frame, you know, there's no unambiguous way of interpreting an abstract element of APHIS. And so,
yeah, so there is this question: without providing the clock, can you say anything about the system, which would be true to anyone, irrespective of the clock that he is using? That's I think the question.
So I mean, that's the thing. So I mean, well, I mean, the total algebra APHIS will of course depend on your total set of degrees of freedom, which are subject to the constraints. So, so there will be information. If I give you a phys, from that information, you will be able to say something about, you know, the degrees of freedom that this describes. There's probably no unambiguous way of doing that, but that's not a problem with relation dynamics per se. That's just something general in quantum mechanics. I'll just give you an abstract algebra. You know, the same algebra will apply to different systems. You know, the same algebra applies to the harmonic oscillator as it does to a free particle, for instance. Right? So, but here, yeah, the statement is that if I want to give within a given a phys that I've constructed, subject to a particular set of constraints, yeah, I can view every element of a phys as a, you know, perspective or clock neutral object, because it doesn't have an interpretation per se before I choose a reference frame relative to which I can write that element, like this white dot here, as a relational observable. So in that sense, it's you know, the choice of clock is a priori, it doesn't have a you know, it's a convention you choose, but it's not a gauge choice. It's just a way of it's a choice of context which you use to interpret your theory. And there exist many different ways in which you can do it, but it's not a gauge choice. And all of these objects inside this a phys, all of them are gauge invariant. All of these objects, they commute with a constraint. So all of that is manifestly gauge invariant. So, so that's I think the answer to your first question. I hope that that answers it. I think then what was your next question? You were asking about.
Yes, I was asking about gauge invariant, that is clock independent dynamical content. But you actually answered to it. You just said that if you just forget about the clock, you get an abstract element of this algebra. And of course, this is not dynamical. It is Dirac observable.
Przemek, I'm very sorry, but we don't have more time.
Okay? Yeah, okay.
I'm very sorry.
Yes, so that's it from my side.
Okay, so last, very short, really very short question, please. So I can't hear any. So let us thank the speaker again for a great talk. Okay, and so.